So I'm going to do a short momentum example. Just went over the basics of momentum, which are in the Monday example recording, so I didn't bother recording that again. So let's take person with mass MP is equal to 100 kilograms, jumps off of a spaceship with a large mass, MS is equal to 100 million kilograms. If the person's jump velocity is, let's say, 5 meters per second, what happens to the ship? That seems like a reasonable question. So the way we're going to analyze this is to assume conservation of momentum, that this quantity P total is equal to 0. So we can definitely say that P total initial is equal to 0. And let's do all y components. So let's erase the vector sign. Now, I have a button for that. So when we go to calculate P total final, that's going to be M person V person final plus M ship V ship final. So the total final momentum is just the values of the momentum of each individual object, and each individual object has its momentum calculated as mass times velocity. So let's just substitute in and calculate what we know. We know that this is 0. We know that this is 100 kilograms. We know that this is 5 meters per second. And we know that this is 100 times 10 to the 6th kilograms, and V ship final is unknown. So obviously we can calculate the velocity of the ship in the final state, and we'll jump to the chase. This is 100 times 5 over 100 times 10 to the 6th with a minus sign because that gets subtracted over the other side. So this turns into minus 5 times 10 to the minus 6 meters per second. Now, this is a calculation of recoil, the same idea that we think of in shooting guns. If you shoot a gun forward, there's a recoil of the gun backwards. The ship is 1,000,000 times more massive. Ends up gaining a velocity that is 1,000,000 times smaller than the person. Now, one of the concerns we frequently have about collisions is kinetic energy. So let's say that V of the ship is equal to, I don't know, let's go with a small value. 10 per second. So that means the kinetic energy of the ship initial is equal to 1/2 times 100 times 10 to the 6th kilograms times 10 per second squared. So that is a lot. So this is times 10 would be 1 billion, times 1/2 is 500 million, times the second 10 is 5 billion. So that would be 5 times 10 to the 9th joules. One, two, three, four, five, six, seven, eight, 9 zeros, yes. So let's do K ship final is 1/2 times 100 times 10 to the 6th kilograms times 10 point, whoa. First of all, it's subtracted. Second of all, it's very small. So let's do 10 minus 5 times 10 to the minus 6 quantity squared. So I'm going to try to do the calculation with as much accuracy as possible, just by typing it in directly into a calculator exactly as it's written there, and I get 4.99 5 000 times 10 to the 9 joules. So the ship's energy hasn't really changed. And we could kind of put this together into a general idea. So we had an interaction between two objects. A person jumped off a ship, and the one object was much more massive than the other. Then the much more massive object basically maintains its velocity. Now, in that case, it makes sense to use the massive object as your frame of reference. In other words, tie your coordinate system to the massive object. So then V ship initial is equal to 0 per second. K ship initial is equal to 0, and K ship final is 1/2 times 100 times 10 to the 6th kilograms times just the 5 times 10 to the minus 6 per second squared. And then that is 0.00125 joules. And that is tiny as compared to the kinetic energy of the person final, which is 1/2 times 100 kilograms times 5 meters per second quantity squared. So that's 2,500 over 2 is 1,250. So as you can see, the person got most of the energy that was released when they jumped off of the spaceship. The spaceship got a very, very tiny fraction of that energy, and that allows us to use the massive object, such as, for example, the Earth, when a person jumps off the Earth, use that as the frame of reference, and basically assume that the smaller object gets all of the energy that is released in that situation. So that's the little example that I wanted to go through. It's kind of related to, oops. Example 9.2 in the textbook, except that I made it much more concrete by having specific values for the person and for the ship. So that is my example, and hopefully that helps you understand momentum a little bit better.